Hello everyone, this is Madhura L from 3rd Sem Brahmo section, and today's subject is mathematics. And today's topic of the subject is curve fitting using linear and nonlinear regression. Curve fitting, a fundamental technique in data analysis and machine learning, plays a pivotal role in modeling relationships between variables, predicting future outcomes, and uncovering underlying patterns in data. In this article, we delve into the intricacies of linear and nonlinear regression, exploring their principles, methodologies, applications, and best practices. Understanding curve fitting. An essential component of data analysis is curve fitting, which allows us to fit a curve to a data set and determine the connection between variables. Regression analysis, both linear and nonlinear, is the main method utilized for this. Nonlinear regression fits a more complicated curve to the data, while linear regression fits a straight line. This article explores both approaches using real world examples and code to demonstrate the ideas and procedures. Linear regression. Linear regression defines the relationship between an dependent variable and one or more independent variables, marrying these two couples in a linear equation, which expresses the best relationship that will account for the linear effect in the recorded data. The simplest is called simple linear regression, where one independent variable is represented by the formula f of x comma beta is equal to beta 1 into beta 2 f of x comma beta is equal to beta 1 x plus beta 2, where dependent variable is y and independent variable is x. Beta underscore 0 is as in linear model, beta underscore 1 is the slope, and epsilon is the error term. Fitting curves with polynomial terms in linear regression. Most common way to fit curves to the data using linear regression is to include decimal terms such as squared or cubed predictors. Typically, you choose the model order by the number of bends you need in your line. Each increase in the exponent produces one more bend in the curved fitted line. It's very rare to use more than a cubic term. And this is the diagram of linear, quadratic, cubic. While the r squared is high, the fitted line plot shows that the regression line systematically over and under predicts the data at different points in the curve. This shows that you can't always trust a high r squared. Fitting curves with reciprocal terms in linear regression. Responses data descends down to a floor or ascends up to a ceiling as the input increases. You can fit this type of curve in linear regression by including the reciprocal 1 by x of one more predictor variables in the model. More generally, you want to use this form when the size of the effect for a predictor variable decreases as its value increases. Because the slope is a function of 1 by x, the slope gets flatter as x increases. For this type of model, x can never be equal to 0 because you can't divide by 0. Looking at our data, it does appear to be flattening out and approaching an asymptote somewhere around 20. For this particular example, the quadratic reciprocal model fits the data much better. The fitted line exchanged the x-axis to 1 by input, so it's hard to see the natural curvature of the data. The scatter plot below, I use the equations to plot fitted points for both models in the natural scale. The green data points clearly fall closer to the quadratic line. Compared to the quadratic model, the reciprocal model with the quadratic term has a lower S value, higher R squared, and it does not exhibit the bias prediction. So far, this is our best model. Nonlinear regression. The nonlinear regression models relate the independent and dependent variables via a nonlinear equation about them. They are helpful where the linear relationship between independent and dependent variables is non-existent. The large number of chums posed by the numerous forms of nonlinear regression models depends on the kind of curve that will fit the data best. An example of a nonlinear model is f of x comma beta is equal to beta 1 into beta 2 plus x of f is of x comma beta is equal to beta 2 plus beta 1 x. Fitting curves in nonlinear regression. Nonlinear regression can be a powerful alternative to linear regression because it provides the flexible curve fitting functionality. The trick is to find the nonlinear function that best fits a specific curve in your data. Fortunately, Minitab provides tools to make that easier. In the nonlinear regression dialog, stat greater than regression greater than nonlinear regression. Enter output for response. Next, click Use Catalog to choose from the nonlinear functions that Minitab supplies. We know that our data approaches an asymptote, so we can click on the two asymptotic regression functions. The concave version matches our data more closely. Choose that function and click OK. Let's look back at the function we chose. The picture makes it easier. Notice that theta 1 is the asymptote or the ceiling that our data approaches. Judging by the initial scatter plot, that's about 20 for our data. For a case like ours, where the response approaches a ceiling as the predictor increases, theta 2 is greater than 0 and theta 3 is greater than 0. Consequently, I'll enter the following in the dialog. Theta 1 is 20, theta 2 is 1, theta 3 is 1. And the key differences between the linear regression and nonlinear regression models are relationship, linear regression and nonlinear regression. For linear regression, linear. Non-linear regression, nonlinear. Equation form f of x comma beta is equal to beta 1 into beta 2 plus x of f x comma beta is equal to beta 2 plus x beta 1 x. And for nonlinear, f of x comma beta is equal to beta 1 into beta 2 plus x f of x comma beta is equal to beta 2 plus x beta 1 x. Model complexity, simple, complex. Predictability, high, variable. Computation, less intensive, more intensive. Convergence, guaranteed with ordinary least squares. Not guaranteed, may require iterative methods. Flexibility, limited to linear relationships. Can model a wide range of relationships. Sensitivity to outliers, high, variable. Applications of linear regression and nonlinear regression. For linear regression, conduct predictions from past data from about scales, stock prices, and the rest of the economic indices. Estimation of phase relationships of physical quantities in scientific research. Easy finance and insurance risk assessments. For nonlinear regression, model population growth in biology as it typically follows the nonlinear pattern. Fitting pharmacokinetic models in medical research. Complex output study in engineering like stress-strain relationships. In conclusion, nonlinear regression versus a linear regression would greatly depend on the nature of the data to handle and what specific requirements of the analysis made. Linear regression shall better fit superficial relationship representing a straight line. On the other hand, data flexibility in nonlinear regression corresponds to higher nature data in handling. And thank you everyone for watching my video. Please do like my video also. Thank you.